6-4, the logistic equation. Mr. Antonucci here, and in this video we're going to talk about how to use logistic differential equations to model and solve applied problems. So here's a standard type of problem. A state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. Hint, hint, that's our carrying capacity. The growth rate of the elk population P is dp dt right here. Notice the domain of P is from 40 to 4,000, and T is the number of years. So we want to write a model for the elk population in terms of T. Because this is a logistic differential equation, we do not have to solve this by separation of variables and go through all the steps. We can go straight to the fact that we know that L is equal to 4,000 because of the 4,000 here. And also they told us that 4,000 was the carrying capacity. So we know P has to equal 4,000 over 1 plus B e to the negative kt. And here the thing is, they did not give us the values of B and K explicitly, but we do know that at 0 years, the initial population is 40. So setting this equation equal to 40 and plugging in 0 would give you 40 equals 4,000 over 1 plus B. And so this is going to give us B equals 99. Now we can rewrite the equation with the particular value of B. We still need K, but we need the particular value of B plugged in before we go any further. So 1 plus 99 e to the negative kt. The other piece of information they gave us was that after the 5 years, the elk population was 104. So in this case, we would set the equation equal to 104 and plug in 5 like this. So 4,000 over 1 plus 99 e to the negative k times 5. Now, solving this will give us a k value of approximately 0.194. So our function p of t is going to be 4,000 over 1 plus 99 e to the negative 0.194 t. So that is our model for this population. The second thing is we want to graph the slope field for the differential equation in the solution that passes through the point 0, 40. We're not going to actually graph the slope field, but we are going to graph the function in Desmos to give you a peek of what it looks like. So we'll bring that over now. Here's the model. So you have P of t is 4,000 over 1 plus 99 e to the negative 0.194 t. I had to adjust the viewing window so that it would go at least above the carrying capacity. Since the carrying capacity is 4,000, I went up to 500. And then I just went out to 80 or 90 on the t-axis. So that's our solution that goes through the point 0, 40. If we zoom in there, you can see that it does pass through that point 0, 40. Okay, zooming back out a little bit. There we go. The third question was use the model to estimate the elk population after 15 years. So if I do P of 15, that gives me 625.67. So that would be approximately 626 elk because we're rounding. The other way you could do it is manually substitute 15 into the function, but we don't need to do that now. And then the fourth question was find the limit of the model as t approaches infinity. Well, we know that the carrying capacity is 4,000, so the limit as t approaches infinity is 4,000. We can see that on the graph. If we graph y equals 4,000, you can see you have a horizontal asymptote there. And also, if you substitute a very large positive number in for t, you're multiplying it by negative 0.194. So e to a very large negative number is going to approach 0 times the 99 is going to be approaching 0 plus 1. So 4,000 divided by 1 is going to be 4,000 for the limit as t approaches infinity. So that's it for this section, guys. Hope that was helpful to you. As always, reach out if you have any questions and take care.